My name is Nir Lahav. Finished my PhD in physics from Bar-Ilan University in Israel, and soon I'm going to start my postdoc in Cambridge University in England about the relativistic theory of consciousness and try to test the predictions of the theory. So I would like to tell you a bit about this theory and what are the predictions. But first of all, a couple of days ago, Daniel Dennett passed away, so I want to dedicate this lecture to him. I don't agree with his ideas about, that our conscious experiences are just an illusion, but still, he was a very important philosopher, and in a way, my theory, this relativistic theory of consciousness, is my answers for the arguments of Dennett and of Chalmers from the other side. And we would like to understand how this 3 pound of meat creates our conscious mind. And it's such a great riddle. But first of all, let's define what consciousness is, so we will be on the same page. So I'm going with the canonical definition that consciousness, if a creature has something that is like to be this creature, then it has consciousness. If there's nothing that is like to be, let's say, discovered, then we don't have any consciousness. So in other words, consciousness is the ability to experience ourselves and to experience the world. And now we reach the hard problem, of course. This is such a great mystery, just like the mystery of quantum measurement or what is dark energy. So we have, from our first-person point of view, I see an apple, for example. This is my conscious experience. But then when someone from the third-person point of view tries to check where is the experience in my brain, we cannot find it. And it seems that the only thing that we can find there are just neural representations or neural patterns, right, that represent the apple and what I experience, but not the experience itself. And this is the hard problem. We would like to have some kind of function, some kind of mechanism, how we can go from neural patterns into the actual experience, how to reduce the experience into some physical neural matter, neural dynamics, or some physical dynamics. But it seems that there is nothing like that. So what can we do here? So this is the gap, the explanatory gap, and this is what we need to solve here. Now, what I try to suggest here, let's say that it reminds me a bit the situation before Copernicus. We had lots of information about the planets, and we thought that the Earth is in the middle of the universe, and then the orbits of the planets were very complex, and a lot of questions couldn't be answered. And then came Copernicus, changed only one assumption, that the sun is in the middle, and all of a sudden everything is much simpler. Now I try to suggest that we need to do something very similar with consciousness, to change only one assumption, and then everything will be much clearer. And the assumption is that today, when we think about consciousness, usually we think that consciousness is absolute. So if you have consciousness, then somehow all of us can check it out and agree that, oh yeah, you do have consciousness. And what I'm trying to suggest here is that, wait a second, maybe we need to change this assumption, and maybe consciousness is a relativistic property, which means that it's relative to the observer dependent, if you like. And this is the approach. I call it the relativistic theory of consciousness. In the paper, you could say I have the conceptual part, the mathematical part, and I try to show how it can dissolve the hard problem, and as we see, also there's some predictions that we can check. But first of all, so what does it mean to have a relativistic state? Or what is a relativistic phenomenon? So let's start from the example, and then we'll go deeper. the first example is just constant velocity. And the constant velocity is a relativistic phenomenon in the sense that, well, you tell me, who is moving here? Is the lady inside the train moves? Or maybe it's the other train that moves? So we actually cannot know until the end of the video, and only then we will see, oh, actually it's the other train that moves. Now, it's not only about the perception here, it's about physics. So it doesn't matter which experiment she will try to do, she will always, the results will always show her that she is at rest. And we cannot distinguish here between someone that moves in constant velocity or maybe they are at rest. We cannot distinguish between those two, and that's why we have here a relativistic phenomenon. Okay? So let's say that we have Alice on the platform, and Bob is in the train, and Bob goes with constant velocity. And Bob will say, I do a lot of experiments here, and I see that I'm at rest, but you, Alice, you and the whole world are going backwards. And Alice will say, no, I'm at rest. You are the one that moves. Who is correct here? Who is right? Both of them, right? Because it's a relativistic phenomenon. There is no absolute answer to the question, what is the velocity? Okay? Of course that it doesn't make sense that the whole world going backwards, right? But from a physical point of view, we cannot distinguish. We cannot do any experiment that will show him that he is the one that is moving. Okay, so we need to remember that it's all about physics here. And so now that's why we need to speak about the observers, and we need to speak about frames of reference. And both of them are different in different frames of reference. Now, what would happen if they don't know that constant velocity is a relativistic phenomenon? Then they will continue to argue about who is right. So he will continue to say, yeah, I'm at rest. And then at some point, Alice will say, oh, come on, you're just delusional. And then Bob will try to counter this, to make some argument against this illusionism, right? And he will say, well, I do hear those experiments, and I see that I'm at rest. If you cannot see it, maybe I have this private property that you just cannot measure, okay? Now, I see your smile, so I see that you see already how similar it is to what we have today in the consciousness study, right? And of course, both of them are wrong. Bob is not delusional and he has no private property. It's just that a constant velocity is a relativistic phenomenon. And now what I'm trying to claim is that the same thing happens with consciousness. So Bob will say, I have phenomenal consciousness. I have quality. But you, Alice, you only have neural patterns. You don't have any consciousness at all. And she will say, no, I have phenomenal consciousness. You have neural patterns. And again, who is right? Well, if consciousness is relativistic, then both of them are right. And we need to speak now about cognitive frames of reference. So when Alice will say, or let's say Daniel Dennett will say, it's a delusion, and then Chalmers will tell him, no, it's a private property. Both of them are wrong in the sense that it's only consciousness, it's only a relativistic phenomenon, and that's it. It's not private nor an illusion, right? Instead, now we need to speak about cognitive frames of reference, which means each cognitive frame of reference is determined by the dynamics of the representations in the cognitive system. So the dynamics of the representations in Bob's brain and in L's brain. So they have two different cognitive frames of reference, and each of them measure reality different. Now, okay, so now this was the example. Now let's go a bit deeper to see how can it work exactly with consciousness. So what I used here is the principle of relativity. This is the basic principle that Galileo and Einstein used in order to develop their theories of relativity, okay? We don't need here, and thanks God for that, we don't need here to use Lorentz transformation and general relativity. It's not about that. It's about the principle of relativity, okay? The basic principle behind, these theories. And the principle is that there is no absolute frame of reference. And because there is no absolute frame of reference, what we have now is just the observers. There's nothing beyond the observers. So then if two observers from two different systems measure exact same results, then we cannot distinguish between them. There is nothing beyond them, right? So they are equivalent. They are in the same, actually the same system and have the same laws of nature. Exactly what we saw with constant velocity. Bob and Alice, from different systems, measure the same results, and we cannot distinguish. Okay, so this is the principle of relativity. But then there is more to relativity, what we call relationalism, which means that also all the natural properties that we see are not absolute as well. They are not intrinsic. They are they manifested by the measured relations. So each observer measures something, measures some relations, and this is how we have some natural properties. So let me give you an example. This time is from Einstein. Einstein realized what we call today the equivalence principle, in which you cannot distinguish between system under gravitational field and system under acceleration. So let's say that we have here this astronaut inside the spaceship, and it's on Earth, and this astronaut releases a ball from her hand, and it will fall because of gravity, right? Now, what will happen if you do the same thing in outer space? No gravity over there, but now our spaceship has acceleration upwards. Okay. Now, when the astronaut will release the ball, for him it will look like the ball is going down, right? Because the ball is floating and the spaceship and the astronaut goes up. So for him it seems like the ball is going down, exactly like what would happen if he was under gravitational field. So Einstein realized that this is the case, that there is no experiment that this astronaut can do in order to distinguish between if he's under acceleration or under gravitational field. So this astronaut will say, hey, I'm not under acceleration, I'm at rest. And I just have here gravitational field. So notice here that again there is a relativistic phenomenon here. And now there is something interesting with the properties that they measure. So think about an astronaut that look at this accelerating system, and the astronaut measures some relations and will say, oh yeah, it's just an accelerating system, right? But then from the inside of the spaceship, the inside of the system, over there, this astronaut will measure different relations. And in those relations, he's at rest under gravitational field. So from here, we have acceleration and no gravitational field. And here, we have no acceleration, but gravitational field, right? So they have different properties. Their relations that they measured manifested different physical properties. And this is the idea. And now, what I'm suggesting is that the same is going on with consciousness. So from the outside, when let's say that Bob is looking at an apple. So from the outside, Alice, the relations that Alice can measure will manifest only neural dynamics. Exactly like here from the outside it will manifest acceleration. But from the inside of the cognitive system, what Bob will measure, the relations there, will be very different. And that's why it will manifest a different kind of physical property. We call this physical property phenomenal consciousness. It's just like that here from the inside of the spaceship, they will measure gravitational field, for example. Okay, so this is the idea here. Now let's see, is it true that we have a very different relations? Do we really measure different relations from the outside and the inside? And the answer is yes. Where from a third-person frame of reference, the only thing that we can do in order to measure, to interact, we need to use sensory devices like our eyes. And then those sensory devices, the only relations, the only measures that they can do are about the neural substrates. And that's why this is what we measure, from a third-person frame of reference. But then, from the inside, we don't have any sensory devices at all. We cannot even measure that we have neural patterns or something like that from our own brain, from our own cognitive system, right? So we measure something completely different. We have a completely different relations, and those relations, the only thing that we can do is to check what are the roles and the relations between one representation and other representations. So when Bob looks at the apple, what are the relations between this apple and, let's say, other apples that we saw before? This is the only kind of measurements that we can do from the inside. So it's very different measurements, and that's why it manifests a very different physical property, consciousness. Now, so we asked in the beginning, okay, what is going on here with the hard problem? And we saw, and now what we see is that we need to take those cognitive frames of reference into account, and then it's just like a coin. You have head and a tail, and both of them are just two different points of view on the same underlying reality. So, and of course, you cannot do a reduction from head to tail, from tail to head, right? So there is no reduction here. It's just two different frames of reference with different measurements, and that's why now we have bridged the gap and dissolved, hopefully, the hard problem. So now the question: how can we check? How can we test this theory? And the answer is that, okay, so we understand that the measurement that we need is to measure some kind of input and all the relevant representations. We need to measure it all at once. So do we know a mental structure that does exactly that? And we do know something like that. We call it cognitive space or cognitive maps, where the brain chooses some coordinates according to what is relevant, and then inside this map we put all the representations. So it can be like, you see, color and shape and the apple that I just saw, and then all the other fruits in this map of cognitive map of fruits, for example. And then we have, so this is exactly what we need, because here we have our input and all the distances, all the relations to other representations. So if we have some area in the brain that creates this cognitive map, over there, I would say, oh, exactly, this is exactly what we need. This is exactly, as I told you before, from the outside we will just see these dynamics, nothing special. But from the inside, those relations will manifest for us consciousness. So now we have a prediction. And the prediction is that every time that we have consciousness, we must see an activation of cognitive maps in the brain. And if we are unconscious, then there should be no activation of any cognitive maps in the brain. And this is exactly what I'm going to test in Cambridge. While we awake or while we have dreams in REM sleep, we have consciousness, and then we should see cognitive maps. And while we are in dreamless sleep, like in deep sleep or under anesthesia, then we should expect to see no activation of no cognitive space. And I'm going to do it with in the consciousness and cognition lab, Professor Tristan Beckenstein, and hopefully next time I will show you the results of that. But now, okay, let's sum up. So the suggestion here is that consciousness is not absolute, but it's relativistic, and then it's not private, it's not illusional, and we didn't speak about it, but zombies cannot exist, and different measurements manifest different properties. The measurements that we use from using sensation, the sensory devices, is the third-person frame of reference, and if we check the relations between representations, then it's different. It's a different manifestation, and we call this consciousness. And cognitive maps is one example of this structure that can manifest consciousness. And of course, there is much more, but we have no time, so please come and ask me. And as usual, funds, as you know, are very limited. So if you want to collaborate with us, or if you just think that this is an amazing thing and you want to give us some funds, please let me know, and you can scan this in order to read the whole paper. Thank you very much.